All right, this is Mr. McCord's chemistry class, Unit 9. We're going to look at assignment number 1, molarity and molality. So we just spent a whole unit looking at how gases have a number of properties like pressure and volume and temperature, and how they can change as the conditions of the gas change, how we can make predictions with calculations using gas laws and stoichiometry. Gases are pretty important to a lot of reactions in chemistry, but just as important, or maybe even more important, are solutions. Now, solutions aren't just a word for how you solve a problem. In chemistry, they also describe a mixture of things like a solid in a liquid, or a liquid in a liquid, a solid in a solid, a gas in a gas, any kind of mixture really that is homogeneous. So there is ideally no difference between how the particles of one substance kind of mix with another. Everything is uniform throughout. It looks all like one pure substance, and we can measure the concentration of one of those substances in the other. Okay, so that's what we're going to be looking at today, how we measure how concentrated a solution is, how much of this is in that. And that will take us into different properties of solutions. Okay, the main way we measure concentration in chemistry is called molarity. All right, the mole of molarity will probably seem a little familiar. Okay, it's our way of measuring concentration of a solute in a total solution. A solute is something that we dissolve in a solution. So if I am putting salt in water, the salt part is the solute. Typically, it's just the smaller amount of something going in something else. So if you're making Kool-Aid or something like that, that powdered drink mix is the solute that you're dissolving in the water. Now, the solution is the name of the mixture once it has been mixed. So what you dissolve that stuff in is called the solvent. So typically, water is going to be our solvent in chemistry. It's kind of the most common, the most popular, the most widely used. It is often referred to as the universal solvent because it is very good at dissolving things. Whether it is salt or drink mix, or even carbon dioxide that you might have in a can of soda or something like that. Okay, so in either case, the solute is just the lesser amount of something dissolved into what we call the solvent, the substance that is holding, in a sense, the rest of that other substance. And together, the solute and the solvent make the solution. Okay, now to kind of go along with the name of how we measure this concentration, molarity has its solute measured in moles. Molarity, moles, kind of makes sense. Okay, so if I am dissolving salt in water, I measure how many moles of salt I am putting in that water. Okay. Now I also measure the total volume of solution in liters. So that doesn't mean I just measure how much water I started with and use that. I'm talking about what volume of solution I have after I've added in my salt or my drink mix or whatever. Okay. Now, there isn't always a huge difference in this. So if you are getting ready to make pasta at home and you've got some water you're getting ready to boil and you throw in some salt, the water level is not going to rise, like, whoa, that was like 6 milliliters or something. It's going to be hard to tell that it's even changing at all. But there can be a difference, especially when we mix a liquid in a liquid. So just to be totally clear, the volume of the solution total is what we want, okay? Not just how much water we are dissolving it in, okay? So we measure molarity as the solute amount in moles divided by the volume of the solution once the two things have been mixed. The solute and the solvent have been mixed. Okay, so we can have an equation for that. So our molarity is often represented by a big M, right? And it's equal to the moles of the solute divided by the liters of the solution. So again, we take moles of whatever we are dissolving and divide it by the liters of the total solution that is made by putting the two together. However many liters we have volume once that all that stuff is mixed. Okay. So when we are calculating the concentration of a mixture, how much something is in something else, we read it out as a molar solution. So if I calculate this out, I have like 1.5 moles of salt in 1 liter of total solution. I'm dissolving it in water or something. Then I calculate it out as 1.5 big M, all right? And that big M is read out as molar, okay? It's not read out as 1.5 molarities or something like that, although that's probably what you would guess. It sounds a little clunky though, so you might be like, oh, okay. So whenever you see 1.5 big M, okay, we read that as 1.5 molar solution, and same thing kind of goes back the other way. We're reading it out as a molar concentration, a concentration of molarity, right? Now you might also say that it has a molarity of 1.5. That's usually fine. But in any case, we're just talking about how concentrated it is. Since we're looking at how many moles of solute are divided by the total volume of that solution, the higher the number, the more concentrated it is, the more stuff we are dissolving in that solution. Okay? If that changes the color of the solution, that means it's going to be a deeper color the higher the number is. If it changes a property of the solution like conductivity, so like in the case of salt, as we dissolve more and more salt in there, it breaks up into the ions that it's usually made of that conduct better and better and better. So the higher the concentration, the higher the conductivity. As we get further into solutions, we'll have other properties that kind of increase with concentration as well. Okay. Now, molarity isn't the only way we measure concentration. Molality is also a way we measure concentration. And these two can kind of be frustrating because they are incredibly close sounding to each other. Molarity and molality are really only one letter apart, and their kind of setup is also pretty similar too, but there is one key difference. Okay, molality measures how much of something we dissolve in the solvent, not in the total solution. Okay, so if I am doing my salt example, I go and dissolve some salt in water. I'm looking at how much water I started with, not the volume of the mixture total I ended with. We still measure the solute in moles, so that mole part of molality is still there at the beginning. All right, we measure our solvent in kg, all right, that's kilograms. So this is a mass measurement rather than a volume measurement. We measure our solvent in kilograms, okay? So our calculation is going to be molality is a little m, and it's equal to the moles of solute, just the same, but it's divided by the kilograms of solvent that we dissolve it in instead of the liters of solution. Okay, that's the real main difference in the calculation of it. We read it out similarly. So 1.5 little m means 1.5 molal solution. Okay, we're calculating the molality, so that is a molal concentration. We don't read it out as like 1.5 molalities, right? So, in essence, the big difference between molarity and molality is the units. Okay, they're still talking about concentration, but molarity is our concentration of moles per liter of solution, whereas molality is our measurement of moles per kilogram of solvent. Okay, in either case, the moles is the same. It's how much stuff we're throwing in to make our solution. But in molarity's case, we're looking at the volume of solution total. In molality's case, we're looking at the mass of the solvent it gets dissolved in. Okay, now I mentioned this before, but a solution does not just have to be a solid dissolved in a liquid, even though that's usually the easiest way to look at it, and it's one of the common ways we do it in chemistry. But we can really dissolve anything in anything else. So the air that you breathe is actually a solution of gases in gases. So if we're looking at the concentration of oxygen in air, you can calculate the molarity or molality of oxygen in a volume of gas. It'd be easier to calculate the molarity because it's easier to calculate the liters of total solution that you are, working with, set out a box or a bottle, a beaker or something that you can measure the volume inside of. Whereas with molality, it would be hard to measure the mass of just the original gas before they get mixed. Okay, so there are kind of advantages to each. We can also dissolve a liquid in a liquid. We can dissolve a gas in a liquid, like I mentioned before with CO2 dissolved in a solution of water and sugar. There's all kinds of stuff shoved in there. Things like rubbing alcohol are a solution of a liquid in a liquid. We can even dissolve a gas in a solid. This is kind of an uncommon one, but one of the ways scientists are working on storing hydrogen gas as a fuel, like if we were going to make hydrogen-powered cars, is to squeeze the hydrogen in between atoms of a big metal, atomic-wise, like palladium or platinum. So you can dissolve a gas in between the atoms of a solid. It's a lot harder and it's a lot more technical, but it technically can work. Okay. Now also, whenever we work out something in a chemical reaction equation and we deal with a solution, we show that something is in a solution of water with AQ, and that stands for aqueous. Aqueous just means in water. So as we move forward, a lot of the solutions that we work with are going to be something dissolved in water. So that's specifically, that kind of solution is what we indicate with AQ, all right, in little parentheses. So like S is for solid, L is for liquid, G is for gas, AQ is for aqueous, something dissolved in water. Also, if we're using just pure water as a solvent, there's a nice little thing about the density of water. 1 gram of water is the same as 1 milliliter of water. Okay, that means that 1 liter is the same as 1 kilogram of water. So we kind of have a shortcut there. So for other solutions, like using ammonia as the solvent, or for a solution that's already been made, like salt water, or a mixture of rubbing alcohol, like 70%, we can't just assume that 1 gram of water is the same as 1 milliliter of water, because in a solution you have other stuff in there that's going to change that density. But if you're looking at the water before it has been mixed, we can make that assumption. Okay, so just be careful not to jump the gun and be like, ooh, okay, I've got 36 milliliters of solution. I'm going to change that to kilograms and calculate my molality.